Suppose that you have a function of multiple variables that depends on like x and y. One way that you can simplify it is to just take one of the variables like y and just make it a constant. So like plug in y equals 7 or plug in y equals 3, and now it's just a function of one variable. And we can do all our regular calculus things with that. But the question is, how can we use that simplification to understand what the original function was doing? We're going to consider a surface where z is a function of x and y, and then fix a single value for y so that f is only a function of x. So what does the graph of this function look like? Since y is fixed and x and z are variables, the graph of this new, more simple function is going to be a slice of the original surface that lives in a plane that's parallel to the xz plane and goes through y naught. Maybe like right here. Okay, I'm going to move it over a little bit. Maybe like right here. There we go. Okay, so let's draw this graph. So I've pulled out the y naught plane. That's the red plane in this 3D picture. So x and z are variables. So that means that this is the x-axis and this is the z-axis. And now this red curve is the graph of the more simple function that depends only on x and z. The rest of this is just Calc 1. From here, I can now pick a value for x and write the equation of the tangent line in the plane through y naught that is parallel to the xz plane. We can calculate the slope of the tangent line. This is the rate at which f is changing. For that single value of y, the rate at which f is changing as x changes. So what we write is del f del x at x naught y naught. So the mathematical definition of the partial derivative is just borrowed from Calc 1. All I need to do is calculate the slope of the secant line and then take the limit as the size of the step goes to 0. So this is going to be the limit as h goes to 0 of f of, now in this setup, I'm calculating del f del x. So this means that x is the variable and y is held constant. So the small changes that we are making happen in the x coordinate and y naught is held constant. Now I'm calculating a difference quotient, so I need to calculate the change in outputs in the numerator and then the change in inputs in the denominator. Let me just clean this up. I don't know if you've seen this before, but sometimes when people will put a colon like that by the equals, what they mean is this is defined to be that. So that's what I mean when I put that little colon. I'm saying this is the definition. There is some other notation for this. You will also see people be lazy and just leave off those x naught, y naught inputs. And then a further way that people will be lazy is sometimes you'll just see subscript notation like that. So people will just write f sub x. This is a bit of a bummer because this is kind of bad notation. Sometimes if people have a vector and they call that like a, b, then they will write v sub x to mean the x coordinate of that vector. So this is a little bit, when you use that subscript notation, it's kind of not great, but it's just so much easier to write. People often do get lazy. So you just need to be mindful of that when you're reading, a math book or a physics book or something, that you don't get subscript notation confused with like, what's the coordinate of the vector versus taking a partial derivative. So just to make sure that you have this definition solid under your fingers, I want you to consider a situation like this, and you can make up your own letters if you want, and try to write the definition of, just pick one of the partial derivatives. In this case, I'm letting w be a function of x and y and z, and take a minute to convince yourself what the definition of del w del y is. This should mean x and z are constant, and we're calculating how the function changes as y changes. Usually students are pretty good at calculating partial derivatives. The trick is to just keep in mind which one is a variable and which one is a constant. So let's just bounce back to Calc 1 really fast. So if you have f of x is 3x to the fifth, and you wanted to take the derivative, you would write df dx, and then now 3 is a constant, and then it's x to the fifth. So on the power rule, I'm going to bring that 5 out front. Then you leave the 3 alone because it's constant, and then you subtract 1 to the power. So 5 times 3x to the fourth. All right, so if you have just like y times a constant, and you were going to take the derivative of that with respect to y, you would write df dy is, so when you take the derivative of y to the power of 1, it just goes away, and all you'd be left with is 7. Okay, so that's the thinking. Just pretend that one of the variables is actually a constant. So now I'm going to do this problem. So I'm going to start with taking the x partial derivative of f. So when the function actually is a function of multiple variables, the way that we distinguish that from just a regular derivative is, that's why we write these like del f. This means that it's a partial derivative, and f depends on more than just the variable that I'm calculating the rate of change with respect to. So del f, and I'll do del x first. So in this process, y is a constant and x is the variable. So I'm basically just treating this y here exactly like I treated that 3 in Calc 1. So this is just going to be 5yx to the fourth. Okay, so you just pretend that y is a constant and just do all the things that you would usually do with a constant. Okay, now let's do del f del y. So in this one, x is a constant and y is a variable. So this is really just y, a variable, times x to the fifth. That's just a constant. So when you take the derivative of y to the power of 1 times a constant, all you're going to be left with is that constant. So in this second example, x was a constant and y was a variable. So this x to the power of 5 was really just like that 7 there. This can be a bit weird, but this is really just y to the power of 1 times some constant x. So when you take the derivative, the y just goes away, and all you're left with is the constant. I just want to work out a slightly more complicated example. So I'm asked, here's the function, and I'm asked to find these partial derivatives. So I'm going to start with the x partial derivative, and I'm trying to just show you the two equivalent notations. So z sub x, you could also write del z del x. So in this process, x is a variable and y is a constant. So I have a natural log. So when you take the derivative of the natural log, it's going to be 1 over whatever was inside the logarithm. And now the chain rule says I need to multiply by the derivative of the inside. So inside this function, I have x squared plus y cubed. Again, x is variable, y is constant. So the derivative of the inside will be 2x. All right. So now in this one, I have a product on the inside. So let me go ahead and take the derivative of the second part of it. So the derivative of cosine is negative sine, and then you leave the inside alone. And now the chain rule says I need to multiply by the derivative of the inside. So in this problem, x is variable and y is constant. So that's x to the power of 1 times some constant. So when you take the derivative, the x is going to go away, and all you're going to be left with is that constant floating on the outside. The pattern that I'm trying to get you to see is that, like, when you have a sort of addition on the inside, it's really obvious that the chain rule, like, is going to put some things with x's in it left on the outside. But when you have like things multiplied together, especially if you have like an x to the power of 1, then what's going to be left over on the outside is probably just going to contain the other letters. So that's just kind of like a little bit like kind of backwards result there. So just keep that in mind, that it can play out that way. And now when I take the y partial derivative, it's all pretty much happening the same, right? You get like a 1 over from the natural log. And then now, since y is the variable, when you do the chain rule, that derivative of the 3y cubed is going to become 3y squared. Okay, now let's think about this one. Y is the variable and x is constant. So I'm trying to do the chain rule and multiply by the derivative of the inside. So I'm trying to multiply by the derivative of x times y to the 7th. So what I get is y is a variable, x is constant. So I'm just pretending that it's like a 4 in front of my y, or a 7 or a 3 in front of my y or something. So all I'm going to do is just a power rule. I'm going to bring the 7 out front, leave the constant alone, and then subtract 1 from the power. Okay, so you can, just like in Calc 1, you could take a second derivative or a third derivative or a fourth derivative. So you could just take derivatives of derivatives of derivatives, as much as you want, and start building Taylor series and the whole lot. But just before we start doing some examples of that, it's not much of an extension. I just want to look at the notation. So when you use subscript notations, you start adding the subscripts on the right side. So f sub xy means you started by taking an x partial derivative and got an answer, and then whatever your answer was, you then took the y partial derivative of that. All right, but with like Leibniz notation, with this del notation, you start stacking the derivatives on the left-hand side. So you can see it's like the same order, right? X then y and x then y. But the cultural meaning of these symbols is del 2f, del x, del y means first you take the y partial derivative and then you take the x partial derivative. So it's a bit maddening that the same notation, like the same letter order, means two different orders of taking derivatives, depending on if you use subscript notation or like Leibniz notation. But I think it's going to turn out to be okay. I'm going to do an example where we calculate these mixed partial derivatives. So technically, when you have second order partial derivatives, there's technically 4 z sub x x. That means first the x derivative, then another x derivative. Z sub x, z sub y y. This means first a y derivative, then another y derivative. We only want these mixed partials. This is z sub xy and z sub yx. Okay, so I'm going to start off with z sub xy. This means first the x partial derivative, then the y partial derivative. So to calculate the x partial derivative, I'm going to have to use a product rule. So the derivative of the first here is just x, so that's going to be 1 times, and then you leave the second alone, so sine x squared plus y cubed. And then the product rule says you're going to have to do plus the first times the derivative of the second. So the derivative of sine is cosine x squared plus y cubed. And now I'm going to need to do chain rule. So now I'm going to have to multiply by 2x, the derivative of the inside. I'm just going to simplify this. So I can just combine like terms, right? 2x and x. I could just make this 2x squared. All right, so I'm calculating z sub xy. So now I've got z sub x. Now I need to take the y partial derivative of this. So here I have a y on the inside of the sine. So the derivative of sine is cosine. Then you leave the inside alone. And then you multiply by the derivative of the inside. So now this is going to be 3y squared. Plus, and then the same logic here, now, except it's going to be minus. The derivative of cosine is negative sign, but the since I'm doing a y partial derivative here, the 2x squared is just a constant. So now when I multiply by the derivative of the inside, oh gosh, I gotta move this over. Okay, partial derivatives get long, but I was multiplying by the derivative of the inside here, this chain rule, so I need to put a 3y squared out at the end. So I can't actually simplify this. I can make this 6x squared y squared, so I'll do that. Okay, great. Now let's calculate the partial derivatives in the other order. Okay, so now I'm going to do y first, then x. So when I look at the original function, this is a constant, that x is a constant, and that x right there is a constant. So the only variable is that y cubed. So this may be a little bit easier. I'm not going to need any product rules or anything. So there's an x in front, and x is a constant, so you just leave it alone. Now the derivative of sine is cosine x squared plus y cubed. And now y is the variable here, so when I multiply by the derivative of the inside, I'm going to get a 3y squared. So I'll probably move that out front and then start calculating the x partial derivative of this. All right, I'm going to need some room here, so I got to get rid of this. All right, so now I'm going to have to do the x partial derivative of this. So I see an x there, and I see an x inside my cosine, so this means I'm going to have to do a product rule. So I'm kind of viewing like this as the product. That's the first, and that's the second. So z sub y sub x is going to be equal to, so the derivative of the first is just going to be, I'm doing an x partial derivative here, so the x is just going to go away and all the rest of that is just constants. So I'm going to have 3y squared cosine x squared plus y cubed, plus now I'm going to have to leave the first alone, so 3xy squared times, now I'm going to have to do the derivative of the second. So this is the second part right there. So the derivative of cosine is a negative sign. So I'll change that to a minus. And then sine x squared plus y cubed. And now I need to multiply by the derivative of the inside. So now I'm multiplying by 2x, the derivative of the inside here. Okay, so I calculated these two mixed partial derivatives right there, and this is what I got. And I want you to just have a look at these two expressions and see if you observe anything about them. That's right. They're equal to each other. And this isn't a unique phenomenon. This is actually an example of something that is true in general. I've seen this called Schwarz's theorem and Young's theorem before. Sometimes that's called the mixed partial theorem. And basically what it says is that, the order doesn't matter. You can do the x partial derivative first and then the y partial derivative, and you'll always get the same answer. If you just do the same number of x derivatives and the same number of y derivatives, it doesn't matter the order that you do them in, which is really fantastic. I mean, when you look at this, you don't really see it coming. This process of taking derivatives, how with all these product rules and chain rules, you would think that if you did it in a different order, you'd get a different answer, but you don't. They always come out the same. So that's really fantastic. And also, it's really, I did double as much work as I needed to do here. I could have, if they asked me to do both mixed partial derivatives, I could have just stopped right there. I know whatever this one is, it must be the same. So it was a little bit of a waste of time, but this is great. And also it comes back later. There is another time that we're going to need this. So please file this away in whatever part of your memory is like you're going to need this later for this class, because it does play an important role in some future content. Okay, so we've done what we set out to do. We have simplified our function of multiple variables into a function of a single variable, and now we can reinterpret that information in terms of the original surface. So the easiest way to see this is The y partial derivative would be the slope of the tangent line if you walked in the direction of the y-axis. So if you walk parallel to the y-axis, how much will you be going up the hill or down the hill? And likewise, the x partial derivative is if you walk in the direction of the x-axis, will you be going up the hill or down the hill? But those aren't the only two directions you could walk, right? I mean, you could walk like this, kind of like in a 45, between the x-axis and the y-axis. So the place that we're in now is how can we calculate the slope, if we choose to walk in a different direction, not just parallel to the x-axis or parallel to the y-axis, how can we completely understand the surface? At a point, how can we decide, am I going up the hill or down the hill, no matter which direction I decide to walk in?